Welcome everybody to the Bhargav second Simon lecture, and today he's going to talk about prismatic cohomology.
Great, thank you. Right, so my goal today is to talk a little bit about prismatic cohomology. And so the way I was planning to do this is I will first introduce a problem that prismatic cohomology solves, explain what shape the solution takes, and then later I'll come back to this something I promised in the abstract, which is about the origins of prismatic cohomology. So somehow the problem that I'm going to explain that it solves is not how it was originally discovered, but I think this is the easier path to take in terms of understanding what it's doing. Okay, so let me sort of begin right away. So I want to maybe, let's say, so the section is going to be called Understanding cohomology, or more precisely, mod P cohomology geometrically. So the motivating question that I would like to try and understand is the following. So let's say, I'll motivate it over the complex numbers. So say M is a complex manifold. Maybe even Kähler. So in this situation, Hodge theory gives you a pretty good geometric understanding of cohomology classes with rational coefficients, or with C coefficients, really. So I'll say it this way: Hodge theory describes the singular cohomology of X, or of M, with C coefficients geometrically, right? Like you have the de Rham comparison theorem, for example, which says that you can represent such classes in terms of differential forms, and then you can go one step further and use holomorphic differential forms, and then use the Hodge decomposition, and you get a pretty kind of reasonable handle on what these classes can look like. But it doesn't answer the question of what happens to torsion cohomology classes, because I'm using C coefficients over here. And so if I have a torsion cohomology class with Z coefficients, this just completely dies. And so that information is lost. And so the question is how to understand mod P cohomology geometrically. So how to study HI of M. Let's say with integral coefficients, understanding torsion cohomology classes with integral coefficients amounts more or less to understanding the mod P cohomology classes for different primes P. And so this is the question I would like to study. And it's a question that comes up in sort of various parts of mathematics. So in number theory, it certainly, I gave an example yesterday where mod P cohomology classes on locally symmetric spaces carry some interesting automorphic information. It's something that comes up naturally in modular representation theory, in understanding sort of intersection cohomology of Schubert varieties and things like that. It comes up even in algebraic geometry, in very classical algebraic geometry, for small values of I, like 2 and 3, understanding these mod P cohomology classes has sort of played an important role in recent progress in rationality questions. So things like, the Brouwer group, for example, produces elements in such cohomology groups. And so this is the question I would like to study. And I would like to propose a partial answer to this question. I mean, it's not as nice as Hodge theory, but it's a partial answer. And I want to give some geometric description of where these classes can live. And it's only going to be in the context of algebraic geometry. So not for arbitrary compact complex manifolds, but rather the ones that come from algebraic geometry. And so let me introduce the relevant notation. So it's the same notation I had yesterday. I'm just recapping it. So C is going to be the p-adic complex numbers, which I called CP yesterday, but since it shows up a few times, I will just abbreviate it as C. It's you take the field of p-adic numbers, algebraically close it, and complete it. So it's a complete and algebraically closed field of characteristic 0. I had this diagram yesterday. So C is a non-Archimedean field. It has a metric on it, and the unit ball inside there is a ring. So we have this ring inside there. This is obtained by inverting P, and then I can sort of set P equal to 0. And I also have to kill all the p power roots of p, but let me not write that. And what you get is f p bar. And I will call this k, just to simplify notation. So capital C is the p-adic complex numbers. It's isomorphic to the usual complex numbers as a field. And little k is an algebraic closure of a finite field of characteristic p. And the geometric object I'm gonna, so I'm gonna try and understand this question over the complex numbers by identifying the complex numbers with this copy of C. And the geometric object I'm gonna give myself is not just a variety that lives over C, but rather something that lives over OC. So it makes sense to reduce it mod P. You can always do this by putting yourself in projective space and clearing denominators in the equations that show up. So let me write it this way. So say X over OC is a smooth projective variety. And so technically speaking, I'm working in what is called a good reduction setting. So I'm assuming that my equations, even after I reduce the mod P, they still cut out something smooth. You can imagine that, for example, the locus of smoothness is governed by some numbers being non-zero, like the Jacobian matrix or the determinant of the Jacobian matrix being non-zero. And it could happen that the determinant is divisible by P, in which case when you reduce mod P, the determinant is no longer non-zero. And I'm throwing that away. So I'm putting myself in a generic situation. And so here's kind of the picture for what one often thinks about in this situation. So here's sort of the base, and the base is, this is an algebraic geometrist picture. So the base is a line. You think of OC as a line. It has kind of 2 points, one corresponding to this characteristic zero field, capital C, and one corresponding to this characteristic P field, little k. And here's X over it. And the assumption is that it's a fibration. So all fibers are smooth. And so the fiber over this point C, so this is just a heuristic picture. So is XC. And the fiber over this point K is XK. It's the varieties I get by just regarding my equations as having coefficients in either C or K. And so we're going to think of this XK over here as a characteristic P partner to this XC. And the way we're going to understand mod P cohomology classes on XC is through this characteristic P partner. Okay, and so actually without further ado, I think I can just state the theorem, and then we'll sort of talk more about it. So here's the theorem. And so this was joint work with Mauro and Scholze. And so in words, what it says is that is the following. So I'll write down a precise statement, but there's sort of one way to think about it. So it says that FP cohomology on XC. So if I have a cohomology class on this complex variety, XC, so you can think of it as an obstruction to integration, just like over the complex numbers, but it's not an obstruction to integration in characteristic zero. It's an obstruction to integration in characteristic P. So more precisely, it's an obstruction to integration of forms on XK. And so the precise statement is the following. The precise statement is that there's a dimension inequality. So I can look at the dimension of the vector space of mod P cohomology on my complex variety, the object I'm trying to understand. And the dimension of that vector space is bounded above by the dimension of a vector space attached to this variety XK in characteristic P, which is this de Rham cohomology. Right. So I don't want to spend too much time on what this object is. Basically, what it means is in the definition of de Rham cohomology, usually so you think of the standard definition is you use all C infinity functions and their differentials and so on. But there's no reason to do that. You can just work with algebraic functions and algebraic one forms and so on. And you get this what is called algebraic de Rham cohomology. And it's a perfectly reasonable invariant. In fact, over the complex numbers, it gives you the correct thing, the correct invariant by a non-trivial theorem of Grothendieck. And in general, over fields of not of characteristic zero, it's the only thing you have. So this is the analog of de Rham cohomology. Well, it is a de Rham cohomology in characteristic P. And so the statement is that if you see a non-trivial cohomology class with mod P coefficients over here, it's going to have some kind of some residue in this vector space over here. It's going to manifest itself by this vector space being non-zero. So, okay. So let me give an example of what information is being captured here, just to give you a feel for what's going on. So let's say P is 2. And my variety in characteristic 0, this XC, is a surface whose fundamental group is a Z mod 2. So I would say it's an Enrique surface. And so the most important feature for me is that pi 1 of an Enrique surface, the Z mod 2. And so because pi 1 is Z mod 2, it's easy to see that H1 of XC with mod 2 coefficients is, well, it's always homomorphisms from pi 1 into whatever, F2 in this case. So this is also just a copy of F2. In particular, is non-zero. And so this inequality over here, which I want to call star just for ease of reference. Sorry, I should have done that earlier. So this inequality tells me that in characteristic P, so in characteristic 2 more precisely, the de Rham cohomology of my Enrique surface has to be non-zero, H1. Just because the left-hand side is non-zero, the right-hand side is non-zero. And so this was actually something that was done classically, known classically. It was due to William Lang and Iluzzi. But it was sort of, the proof was not so simple. There's a classification of Enrique surfaces in characteristic 2 by Bombieri and Mumford. They fall into 3 types, and they go through each type, compute the cohomology group, and observe it's non-zero. But it was always regarded as a pathology of de Rham cohomology in characteristic P, that this H1 is non-zero, contrary to what happens for a complex Enrique surface. And so what this theorem is saying is that actually maybe you shouldn't think of it as a pathology. It's just a reflection of the fact that there's torsion in the cohomology of a complex Enrique surface. And this is going to be reflected in the differential geometry of Enrique surfaces in characteristic 2. Okay. Are there any questions so far, by the way?
Here's a question.
Yeah.
So if I want to understand the variety over a complex number, do I use an abstract field isomorphism to this C, and then everything will be the same? Right.
It's just an abstract isomorphism of fields. And so any information. So, okay, maybe one question you could ask is that if I don't choose such an isomorphism, what does this even mean? And so then I would say you define it using étale cohomology. But then you prove that once you pick your isomorphism between my C and your C, the étale cohomology groups identify with the singular cohomology groups. So then you can forget about the étale stuff.
Yeah, thanks.
Mm-hmm. Right, okay. And so let me just make a couple of remarks on this theorem. So first of all, the obvious question I think should be that, is it actually an inequality, or are we just stupid and it's actually an inequality? And so the answer is it is an inequality. So star can be strict. And sort of we wrote down some examples where this happens, but at least here's a plausibility argument for why you might expect star to be strict. The relation between XC and XK is that XK is obtained from XC by reducing the equations mod P. That was the definition of XK. And so there could be tons of different equations in characteristic 0 that reduce to the same equation mod P. And so there are lots of different XCs that give you the same XK. And so there's no reason that the different XCs in characteristic 0 need to have the same cohomology just because they have the same partner in characteristic 2 or characteristic P. And that's in fact what happens. So we find an example of 2 different XCs in characteristic 0, which have different topologies. So one of them doesn't have a pi 1 and the other one does have a pi 1. but they specialize to something in characteristic P, which is isomorphic. And so that leads to a counterexample. Oops. Yeah. So yeah, I'll just say star can be strict. The second remark is that it was sort of, I mean, this is kind of a well-studied thing in p-adic Hodge theory. So I will say the star was known previously in some special cases. In the special cases where it is actually an equality. By work of Faltings and Caruso separately. But the assumptions were restrictive. They were there were basically two sets of assumptions. One is that the dimension of the variety has to be smaller compared to P. So Enrique surfaces in characteristic 2 are not covered because 2 is not smaller than 2. And the second assumption was that X has to be defined over a field which is not very ramified. So you can't have lots of P power roots of P, for example, in the defining equations. Okay. Great. Are there any questions so far? So my goal for the rest of the talk is to explain roughly how this inequality is proven. And maybe the inequality itself is not that interesting. The mechanism by which it is proven is probably more interesting. And so I want to focus on this mechanism. And the mechanism is prismatic cohomology. And so roughly what this does is that so it's a new cohomology theory that interpolates between these guys. So we're going to construct a one-parameter family of cohomology theories whose sort of generic value is this one, and whose special value is this one. And then the inequality we want follows by just linear algebra. But let me sort of get there slowly. So let me talk about the prismatic cohomology of a point. So it's already interesting when the base is a point. And so I want to discuss this separately. And so in this case, what I'm about to describe is a construction of Fontaine. It's one of the early constructions that started the subject of p-adic Hodge theory. And what I'm about to talk about is just sort of baby algebra. So let me try to motivate it by the following observation. So if R is a commutative ring of characteristic P, meaning P is equal to 0 in R, then there is an endomorphism phi from R to R, given by sending an element to its p power, the Frobenius endomorphism. So the statement is that this is a ring endomorphism. And it's obviously completely natural in R. And by naturality, somehow the Frobenius endomorphism acts on anything you would write down in characteristic P algebraic geometry. And this is actually what is one of the most powerful tools in the subject. So there's an entire subject of it's called F singularity theory. F stands for Frobenius. And the idea is to measure singularities of a variety using sort of behavior of the Frobenius endomorphism. And it's very useful. So a lot of the recent progress in birational geometry in characteristic P, for example, relies on this study. But what I want to do is I want to focus on what happens if you try to copy this in mixed characteristic. So the question is there something similar if P is not 0? So in particular in mixed characteristic. And okay, so the answer is obviously no, because if there was something this basic available in mathematics, everyone would have heard about it. But let me just give you an exercise if you're so inclined. So the exercise is to show the following statement is false. Or it's a non-existent statement. So the exercise is to show that there is no endomorphism phi from this ring OC that I've been talking about to itself with the property that phi of F is congruent to F to the P mod P. So not only, I mean, obviously raising to the P power doesn't work because everyone knows that it doesn't respect addition unless you're in characteristic P. But the statement is that there's no way to futz around with it so that it works just mod P and not on the nose. There's no ring endomorphism that satisfies this property. And it's not so hard to prove this. You just use the factorization of P as square root of P times square root of P and see what Frobenius will tell you, but I won't do the exercise. And so you might assume that this is the end of the story. There's sort of no way to sort of take Frobenius in characteristic P and sort of try and lift it to something in mixed characteristic because of this non-existence result. But Fontaine actually found a beautiful way to fix this. That beautiful way is going to point us in the direction of prismatic cohomology. So let me discuss its solution. So what he said is that, okay, well, it doesn't work for this ring, but there is a closest approximation to this ring where there is such an endomorphism. And this closest approximation is actually completely natural in the original ring. And so let me write down his definition and then we'll unravel it. It's a maybe slightly complicated thing to look at, but I think it's worth staring at. So it's called A-inf. And it's defined to be the following. So I'll write down a series of symbols. So it's the width vectors of an inverse limit. And the inverse limit is you take this ring OC, you reduce it mod P, and then you hit it with the Frobenius. Okay, so this is a construction I can do. I don't expect you to know what the width vectors are. It's not really relevant for my talk, but I just wanted to give you a precise definition. So the OC mod P is a ring of characteristic P. So I have a well-defined Frobenius over here, as I was just talking about up here. I can take the inverse limit along that. What you obtain is called the inverse limit perfection of that ring. And then there's a general procedure that Witt came up with for taking rings of characteristic P and producing rings of characteristic 0 out of it, which is called the width vectors. And so, okay, this is a bunch of words and it gives you some object, but what does it actually look like? How do you understand what the structure of the string is? So maybe the first thing I should observe is bifunctoriality of everything. So whatever the width vectors are, they're a functor. And my input object was an object of characteristic P. And so it has a Frobenius endomorphism. And therefore, by functoriality, I get a Frobenius endomorphism of A-inf, which is called phi. So here are the sort of relevant facts about it. And then I will try to draw a picture for what it looks like. So how do I say? Okay, so what is A-inf really? So I'll tell you two things about it. So first of all, phi from A-inf to A-inf, the map that I just defined through this abstract procedure is a lift of Frobenius in the sense that it satisfies the congruence I mentioned earlier, that phi of f is f to the p mod p. So if you like, I have taken a ring which did not have any interesting endomorphisms, like OC over here, and I have rigged it to produce a ring which now does have an interesting endomorphism. It's this one. Moreover, it's closely related to the ring I started off with. And the relation is that it's a one parameter deformation of OC. So there exists an element U in A-inf such that, well, first of all, it behaves nicely under the Frobenius, and maybe you can ignore this point for now. And more importantly, A-inf mod U minus P is isomorphic to OC. Okay, so this is what I wanted to get at. So this was the ring I started off with. I told you that it did not have any interesting endomorphisms in this exercise. And now we produced a one parameter deformation of it in the sense that we produced a ring with the property that when you go mod an element, you get the ring I started off with. And this new ring does have an endomorphism, which deserves to be called the Frobenius. And so this was Fontaine's idea of taking OC and sort of fattening it so that you see something which has a Frobenius action. And so in modern terminology, this triple A-inf, comma, its Frobenius endomorphism, comma, this element, or rather the ideal generated by this element, is an example of a perfect prism. And this is the closest I'm going to come in this lecture series to defining what a prism is. So it's a certain tuple where you have not just a ring, but rather a ring with an endomorphism and an ideal that satisfies some relation. Okay, so I'm sorry, this is kind of technical, but I want to draw a picture now to maybe make it clearer to think about. So to a first approximation, what do we know about A-inf? Well, whatever it is, it has this element U in it. It has the element P in it just because it's a ring. And it turns out you can more or less pretend that it just looks like a power series ring on U, and you don't lose that much information. So the idea, heuristic maybe, is that A-inf sort of is, I don't know what symbol to put over here. It sort of looks like a formal power series ring over ZP in the variable U. This is not literally true, but it's close enough to being true for many applications. And so therefore you can picture it like so. I'm going to picture it on the P, U axis. And so this is the U axis. This is the P axis. So I guess I'm doing another thing here, which number theorists often do, which is you try to pretend that the prime P is actually a variable. So remember how I said yesterday that you can think of elements of ZP as formal power series in P. So P itself kind of looks like a variable and U is a variable. So ZP adjoint U is like a two variable object. And so you can draw it in the plane. And then it has a bunch of divisors on it. So I will single out two of them. So this is the divisor, which is U equals P. And it turns out to be important to contemplate another one, which is U equals P through to P. And then there is a Frobenius that acts on the picture because there was a Frobenius over here. And so I can, it acts on A-inf and therefore it acts on this picture. And so it turns out it goes in this direction. Five. And so what I'm going to do is I'm going to now explain what prismatic cohomology looks like in terms of this picture. So this is going to be, A-inf is going to be the prismatic cohomology of a point. And so the prismatic cohomology of a general object is going to be a module over A-inf. And so we're going to be able to think of it in terms of this picture. It's going to sort of have various values over regions in this picture. Okay. So that was kind of a fast introduction to Fontaine's A-inf. Are there questions about it? Again, I'll fill in this picture more as I go along. Okay, so let me talk about prismatic cohomology in general now. So as I said, this A-inf is the answer for what the prismatic cohomology of X is when X is a point. And so in general, we expect to produce modules over this ring. And let me just tell you what the important features of those modules are. So I'll state it in the form of a theorem. So I go back to my original setup. So I had my X over OC, which was this smooth and projective variety. And so to this, we attach a bunch of a cohomology theory. So we'll denote it as H star sub prism of X. This is a cohomology theory valued in finitely generated modules over A-inf. Sorry, did that stop writing or is it just on my screen?
No, it looks like it stopped.
Okay, so my impression is that the standard solution to this problem is to stop sharing and restart sharing. So maybe I'll try that again. Great, that worked on my screen at least. All right, so so this is a cohomology theory that's valued in modules over this ring, and it has the following two isomorphisms that I'll write down, which relates it to existing cohomology theories. Satisfying A So A describes what happens on this part of the picture. So if I said U equals to P in this cohomology theory, which means, formally speaking, I extend scalars along the map that kills the idea of U minus P, then what I get is de Rham cohomology. So if I take H star A of X, or A star prism of X, tensored over A inf with A inf mod U minus P, and I remind you this one was OC. This is the way my parameters are chosen. I get de Rham cohomology. And on the other hand, what I can do is I can also invert this element instead of killing it, which is sort of something happening in the orthogonal direction. So let me tell you what happens over there. So if I take H star prismatic of X, tensored over, well, I don't have to say it this way. I can just say it this way. Invert U minus P. And then let me also complete it in the p-adic sense. Then what I get is the singular cohomology of the complex fiber with ZP coefficients with the modification with the caveat that I have to extend scalars to whatever my ring is. But it's just like it's a torsion-free algebra. There's nothing sort of happening there. And so in terms of this picture, let me just fill that in. So what I'm saying is that over here, I'm getting de Rham cohomology. If you sort of think a little bit about what inverting U minus P and completions are doing, over here, I have, so in this region, I guess, I have the singular cohomology with ZP coefficients. In particular, I want to focus on what's happening just at the level of the x-axis. So on the x-axis, what I get is the FP singular cohomology of XC away from the origin. And at the origin, which is where all the interesting action is happening, what I get is the de Rham cohomology of XK. And so if you believe that there is a picture like this, then sort of if you stare at what's going on at the x-axis, what it's telling you is that you have a one parameter family of cohomology theories parameterized by the x-axis for generic values of the parameter where you have a singular cohomology of XC. And then for a special value of the parameter, namely at the origin, what you have is the de Rham cohomology of XK. And so whenever you have, if you have a family of finite dimensional vector spaces, then for generic values of the parameter, the dimension is constant. And then for special values of the parameter, the dimension might go up. So a typical example might be you look at the co-kernel of a matrix, and the matrix has polynomial entries. So for generic value of the entry, the matrix might be invertible. And so the co-kernel is 0. But for a special value of the parameter, the matrix might not be invertible. So the co-kernel is not 0. And that's the kind of thing that's happening over here. So just staring at the x-axis from this comparison theorem implies the previous inequality I'd written earlier. So, oops, go back to black. So staring at the x-axis, or sorry, whatever was the u-axis. Plus linear algebra implies this inequality star from before. And so that's what roughly what prismatic cohomology does. So it produces this kind of deformation that lives over A inf, and there are these two specialization isomorphisms that sort of fit in this picture, and they allow you to deduce this inequality star that I mentioned earlier. Yep.
Bhargav, when you write, I have two questions related. When you write the red H star XC and you put it in that triangle, do you actually mean that it's all over the place, or just?
Yeah, it's all over the place. It's like an open set.
Yeah, and when I see this line U equals P over 1P, you could do that too, right?
Yeah, so actually I was about to comment on this, right?
Okay.
So Right, a natural question might be that what happens over other parts of the picture? Do you get other cohomology theories that are interesting? And so I don't want to go too much into this, but I want to at least talk a little bit about these two arrows that I've drawn but not labeled. So what happens on the, first let me tell you what happens on the y-axis or on the p-axis. So what you get over here is called crystalline cohomology. And so again, this was a classical invariant that was defined in the 70s. And I'm just pointing out that it's in this picture. But what you get over here on the u equals p to the 1 over p axis actually seems new. So if you're calling this Hodge state cohomology, and it turns out to be quite useful in some commutative algebra applications that I'll get into tomorrow or Thursday. And then, I mean, I think that more or less describes what's going on. Like this stuff over here covers kind of this part of the picture. And over here, sort of the theory was, we know how to describe it explicitly over here. And so at least point-wise, I've covered the whole space when I do it this way. Does that answer your question, Mark?
Yes, thank you. But since I'm curious, there are other lines, other curves.
Yeah, I mean, I think there are questions we don't know how to answer, certainly. Like I could sort of keep tilting this. I can sort of keep doing this. And I don't really have a concrete description of what you get there. It's just the first one we were able to describe, and we got some mileage out of it.
Yeah. Thank you.
Mm-hmm. Other questions? Okay, so that was my attempt at telling you what prismatic cohomology is, and also what it does for you. So what it is that it's a cohomology theory which has these comparison isomorphisms. And what it does for you is that it gives you this inequality star that I started off the talk with. What I want to do in the rest of the talk is to give you a little bit of context. So where did this actually come from? As I said, we were not trying to prove this inequality star, nor were we trying to interpolate between cohomology theories. There was kind of a more precise inspiration for this. So there were actually two essentially unrelated motivations for wanting a cohomology theory that looks like this. And so the first one, which belongs to sort of abstract p-adic Hodge theory. And I will be vague in this part, but I just want to give you a flavor for what the questions were. So in abstract p-adic Hodge theory, in around, I didn't write the date, in the mid 2000s, maybe 2006, Mark Kissin came up with a really kind of amazing construction. And so let me tell you about what he did and why it's related to this prismatic stuff. So say X is defined over ZP. So I'm in some setup where I live over a small field, not over a big field. And so there are Gala actions available, monotomy actions. And so what this implies is that this absolute Gala group, GQP, that I discussed yesterday, acts on the singular cohomology with ZP coefficients. Let me call this L for lattice. And so maybe I should actually mod out by torsion. So in Kissin's theory, he always mods out by torsion. And so this is an example of a Gala representation of GQP. And it's somehow like the most important Gala representations in number theory are of this form. You look at the cohomology of a variety, and it gives you a highly interesting and non-trivial representation of the Gala group. And an important question in number theory is to understand these Gala representations explicitly. Like, how do you concretely describe them? Like, a priori, it's just some like humongous group acting on some module in this case. And so what Kissin did is that he attached to this a linear algebraic object, which is called the associated Kissin module, which looks like so. So Kissin says the following. So there exists a natural A-inf module, which I will call M of L, attached to L, with the property that M of L mod U minus P, in the sense I had earlier, is closely related, at least. It's not the same, but it's closely related to the de Rham cohomology. Right, so in my comparison isomorphism for prismatic cohomology, I had a similar statement. I took prismatic cohomology and I modded out by U minus P, and I got de Rham cohomology over here. And so Kissin is producing a module over this Fontaine ring A-inf with the property that when you mod out by U minus P, you get de Rham cohomology. Or it's closely related in the sense that they're the same up to torsion, because in his theory, he's always ignoring torsion. And so then a natural question was, can you actually do all of this geometrically? And I think a lot of people had asked this question. So can one construct M of L geometrically? Meaning geometrically from X rather than from this Gala representation. And there are many reasons why you might want to do this. One is that this throwing away the torsion is kind of a bad operation, and it often ignores some information, and so you don't want to ignore it. The other reason is simply that, well, if you had this, then you might also imagine doing something like this with mod P coefficients rather than the ZP coefficients, integral coefficients. For Kissin's theory, it was kind of crucial that he was working with torsion-free objects. And so then the answer is, well, yes, the answer is you use M of L as the prismatic cohomology of X. And so that was actually the original motivation, at least for me, for trying to find this A-inf module, which was to try and sort of geometrize this construction of Kissin in the hopes of understanding it better. Okay, does that make sense? Any questions?
So hot shear means Gala action, right? In some sense.
Sorry, can you say that again?
So-called, we call p-adic hot shear corresponds to the Galois group action. That's where the name.
Right. So p-adic hot, well, I mean, it's like abstract hot theory. What does it actually mean? Is it the study of the cohomology of varieties, or is it the study of hot structures? So there's kind of two sides to p-adic hot theory. There's the geometric side, concerned with comparison isomorphisms between various cohomology theories. And then there's the abstract side, which is like studying what the coefficients look like. And so this is on sort of the abstract side. Like on one side, you have things like Gala representations. On the other side, you have things like modules with some finitely many operators you can describe explicitly. And you try to prove some equivalences between those categories. Right, I mean, I guess I should say the reason this stuff is useful in number theory is that once you describe this Gala representation explicitly through linear algebra, you can do things with it. So one of the things that number theorists want to do is study deformations of Gala representations. And this is hard if you just have like some abstract representation of this group. But if you just have like a vector space with a couple of operators satisfying some relation, you can try to understand what it means to deform them by hand. And this turns out to be quite fruitful. Right. So that was one motivation. And the other motivation was from homotopy theory. So more precisely, it's Hesselholt spot periodicity theorem. And so Hesselholt had observed that this kind of remarkable construction of Fontaine of A-inf actually has this. You can get at it from pure homotopy theory rather than through arithmetic as I did. So so what he says is the following. So given a commutative ring R, you can, so I mean, this is not Hesselholt, this is just background. So define something which is called TP of R. TP stands for topological periodic homology. It's not relevant to follow the details of what I'm about to say. I just want to tell you a story. And so in symbols, what this is you take what is called THH of R, and then you apply the Tate construction to it. And so what does that mean? That means that you take R and you tensor it with R over R tensor R. And the bottom tensor is taking place over the sphere spectrum. So that's the place where homotopy theory creeps into the situation. And then you do this thing called the Tate construction, which is whenever you have an object with a circle action, you can do something called the Tate construction. Okay, so this is some horrible looking thing that if you first encounter, you would not know what to do with, and it's totally fine, it's not relevant. The sort of important thing I want to emphasize is that this is naturally an E-infinity ring spectrum. Meaning, so it's the kind of object that algebraic topologists want to study. and it's closely related to the algebraic K theory. And that's why, in fact, you want to study this. So it's closely related to algebraic K theory of R. And so it's generally considered to be the case that there are these approximations to algebraic K theory that are more computable, and TP is one of these approximations. And so it's something you want to understand. And Hessel was trying to understand this in the simplest case, in the case of OC. So what Hessel proved is the following. So he computed what the homotopy groups are of TP of OC. And what he observed is that you get the spontaneous ring A out of it, except you get a two-periodic version of it. So A for join U comma U inverse, where the degree of U is 2. So this construction of Fontaine that took OC and produced A out of it, which I told you about earlier, was this procedure of Witt vectors, the inverse limit of Frobenius on OC mod P. There's a completely kind of different way of producing A out of OC, which is to put it through this algebraic topology machinery and look at the coefficient groups that come out of it. And so if this is meant to be an approximation to the algebraic K theory of OC, a natural question is what happens if you have not just OC, but algebras over OC? So this is, so to speak, the case of a point. And you want to understand what happens if you have a general object. And so that was the motivating question. So the question was, can one do something similar? For TP of X, for X over OC as before. Meaning you want, so this is something that you can always define by more or less the same formula. And it makes sense, but you want to describe it explicitly in terms of things having to do with A. And so the answer that I mentioned this in some form at the end of my talk yesterday is that, yes, you can do this. So there is a filtration on TP of X, and the associated gradient of the filtration is given by prismatic cohomology. So answer is yes. There exists a filtration on TP of X whose associated gradient is given by prismatic cohomology. And so this was one, this was one reason we were looking for a prismatic cohomology. So if you don't have prismatic cohomology, it doesn't even make sense to say this, but you were looking for some cohomology theory which filtered TP and played the same role that for TP of X as A does for TP of a point. And so that was the second motivation. And two motivations are essentially orthogonal to each other, but they led us to the same object. Okay, so that was my attempt at telling you a little bit about the history of where this stuff came from. Are there any questions? Okay, so let me just make a remark now. So it might be slightly confusing because I haven't actually said what the cohomology theory is. I've just told you what it was good for and where it came from. So I didn't tell you how to construct it. So by now there are 3 constructions and they're each kind of different. So there exist 3 constructions of this prismatic cohomology. The first one is sort of through p-adic Hodge theory. More precisely, it uses what is called the Falting's almost purity theorem. If you're sort of looking at the papers, this is the paper BMS1. There's a second one where we were able to sort of, historically this came second, so we were able to find this filtration on TP and use it to actually define prismatic cohomology. So we constructed a filtration on TP and then defined prismatic cohomology as the associated gradient and then checked that it has all the right properties. And so this is, the second one is through topology. So through TP. And this was there's a follow-up to this paper by the same 3 authors I mentioned before, Patmore and Scholze. And then finally, probably the most useful one is the most recent one, which is where the name Prismatic comes from. So it's through what is called the prismatic site. In some sense, this is the most elementary construction. We just write down a class of, so if you're familiar with some site theoretic definitions of cohomology, like crystalline cohomology, it has a very similar flavor. It's extremely explicit and doesn't use any of this fancy machinery like the almost purity theorem or homotopy theory. And it's also simultaneously the most general. So the previous 2 constructions have some restrictions and they're applicable. This one is the most general, and so probably this is the most likely to be more useful in the future. So this is me and Peter. And so if you want to understand how this theory is actually defined, I suggest looking in one of these papers. I will not be able to actually explain it in these talks. And so in the last like 7 minutes or so, what I wanted to do is I just wanted to tell you what other people or what people have been doing with this cohomology theory, like what kind of applications it has. So other applications and follow-ups. So the first one is this already came up when we were writing this paper, which is there's this notion of Q deformation in combinatorics. And there's a notion of a Q deformation of the de Rham complex where you take the de Rham complex of a variety, but then you sort of deform the de Rham differential by changing the derivative to a Q derivative. And what this theory allows you to do is it allows you to prove that these Q deformations are actually coordinate independent, which is not at all obvious from the definition. So there's a notion of a Q de Rham complex attached to any variety equipped with a set of coordinates. The actual complex you write down visibly depends on the coordinates. Like it's not at all clear how to trace what happens if you just change x to x plus 1 in the coordinates. Nevertheless, it's a theorem that the quasi-isomorphism class of the complex is independent of the choice of coordinates. And the only way now I know how to prove that theorem is to sort of go through this formalism. It's not so clear how to do it otherwise. And there's a bunch of natural follow-up questions that remain to be answered. So this machinery also gives you like, there's a notion of a Q Gauss-Manin connection. And so then if you're sort of so inclined, you might want to understand like, well, are the solutions to the Q Gauss-Manin connection given by the Q hypergeometric functions that people have studied in other contexts? If you believe that the 2 appearances of Q deformations should be related, then this should be the case, but I think it's still very much an open question. Other things one can do with it are sort of, well, I mean, maybe it's not surprising, it's like K-theory calculations. And so maybe I'll just mention one sample calculation that comes out of it, just to write down an actual theorem. So the theorem is the following. If you look at the homotopy groups so if you look at the K-theory groups of OC mod p to the n, for any n, then these are concentrated in even degrees. So they vanish for odd values of star. Previously, this was known when n was 1, but n equals 2 already was wide open. And basically, this is related to the fact that we understand nothing about algebraic K-theory. Like we understand very little, and this gives you at least one new tool you can try to use to compute algebraic K-theory. There are other calculations that people have done, but I think this was the simplest one for me to write down. Maybe in the notes that I send Dima, I will mention a couple others. The third thing I wanted to mention was sort of calculations of cohomology. So calculations of singular cohomology. In p-adic geometry. So more precisely, what I mean is the theory that I've described is not only something that lives, that makes sense for algebraic varieties, but actually it makes sense for p-adic analytic objects. And there are many p-adic analytic spaces whose cohomology we do not understand. And so this gives you one new tool to try and understand the cohomology of those spaces. And this was carried out in one example by Kolmez, Daspinescu, and Niziol. And what they showed using this prismatic machinery is that the cohomology of the p-adic upper half space with ZP coefficients is torsion-free. So this is what's called the p-adic or Drinfeld upper half space. So again, the precise statement of which variety that they're talking about is not that important. I'm just trying to explain that since you have a new tool for computing cohomology, you might hope that you can get some mileage out of it. And this is one example where you can. Okay, and then maybe the last thing I wanted to say is more of a, so it's not an application necessarily yet, but it's more about what I think will happen in the future. And so this theory gives you a good definition of a mod P crystalline Gala representation. So Gala representations are things we understand, but there are these conditions that one wants to impose on them. One of them is being crystalline. And this is a condition that's sort of only defined rationally. But there are various reasons where you want sort of something that makes sense with mod P coefficients. And this machinery of the prismatic site allows you to give at least a candidate definition here. And so Drinfeld recently has a paper which is called Prismatization, where he describes a certain stack. And the correct answer to what a mod P crystalline Gala representation is should be a vector bundle on a stack. But this is still very much work in progress. So I think people are still trying to understand the final story there. Okay, so I think this is all I wanted to say in my talk today. I apologize, it was a bit disjointed, but I'm very happy to answer any questions.
Thank you very much. Any questions? Can I ask a naive question? So why is it called prismatic?
So the professional answer is that a prism disperses, like there's this kind of famous picture, right? You have a ray of light coming in, and then it sort of spreads out all over the place. And so our thinking was that the ray of light could be like X, and then this is the prismatic cohomology of X, which is sort of spread out all over the place. And then each of these individual rays are the constituent cohomology theories. And this is this machinery of like A and the practical answer is, the non-professional answer is that we're both Pink Floyd fans. And this was a nice way to work it in.
What was the second thing you said?
Peter and I are both fans of Pink Floyd.
Oh,
and there's a famous album cover with a prism on it, The Dark Side of the Moon.
So is prismatic cohomology as per the axioms of vague cohomology theory?
So my understanding of vague cohomology theories is that they're only with coefficients in a field. The axioms only make sense for something which has coefficients in a field. And here the coefficients are in this kind of big ring. So I'm not sure how to answer that.
Oh, I see. So yeah, like the question doesn't exactly make sense. Okay.
It has all the expected features. So there's Poincare duality. There's things like cycle classes, there like trace formulas and so on.
So and the like a trace formula means like you can still calculate. Oh yeah, because you can still like calculate dimensions of these things and then take like the alternating sum or something, and that should work. I see. Mm-hmm. Yeah. And that would be dimension over what though?
Like rank over A, for example. A is a domain, so I can rank over that.
You can take like the rank over these things. I see. Mm-hmm. Cool. Yeah.
So how are algebraic cycle classes special?
How are they special? Oh, you mean what conditions they satisfy?
Yeah.
Right. So there's an aspect of the story I didn't touch upon. So this cohomology theory has a bunch of extra structure. So there's a Frobenius action, And there's also a filtration on it, which is called the Nygaard filtration. And the cycle classes satisfy the condition that they behave predictably under the Frobenius. So a codimension I cycle is scaled by some specific element to the ith power times the original cycle. And they live in a codimension I thing lives in fill I of the Nygaard filtration. So this is not the Nygaard filtration is some version of the Hodge filtration in this setting. Having said that, there is no hope of having an analog of the Hodge conjecture in this setting. Like these conditions that I just said do not pin down what the cycle classes are. They're just constraints that cycles have to satisfy.
So presumably you have plenty of classes that satisfy that and are algebraic.
Right.
What about things like hard Lefschetz or the Lefschetz hyperplane theorem, stuff like that?
Lefschetz hyperplane theorem should be fine. I mean, this theory, the way you prove theorems about this theory is by deformation. So it's a deformation of de Rham cohomology. So if you can do something in de Rham cohomology and it's like a cohomological statement that something vanishes in a bunch of degrees, it will follow for this theory as well. So I think the Lefschetz hyperplane theorem should be fine. Not sure about hard Lefschetz. This is an integral theory and hard Lefschetz is not true integrally. So I'm not exactly sure what to say.
Other questions?
Bhargav, I have a question. So the crystalline cohomology of like an affine variety tends to be infinite dimensional, say over ZP. Is that also the case for prismatic?
Yeah. In this world, somehow, I think you don't expect to produce a finite dimensional answer for something affine.
Okay.
It's like functions on a Stein manifold. I mean, that like tends to be huge.
Thank you.
Do you also have pairings, like intersection pairings and?
Well, there's a ring structure on cohomology. And the top cohomology is like something that you can identify canonically. So there's at least cup products and Poincare duality. I don't know if that.
But what I mean is that, for example, do you expect these intersection pairings to be integral in some sense, more integral than?
Right.
For algebraic cycles, of course.
I'm not sure. I haven't thought about it. I mean, there are special things that happen for cycles, for cohomology classes attached to cycles, or to, let's say, Chern classes of vector bundles. And so maybe there is something to say in that direction, but I just, yeah, I don't have anything concrete right now.
Bhargav, sorry, I also had a question. So, so you earlier when you talked about it, you said that there's sort of this restriction, right? That mod P, when you go to this K, things still have to be somewhat nice. So I cannot like take an arbitrary complex thing, sort of identify C with CP, and then get something, right? Like.
Yeah, so that was right. So that's a simplification I made for this talk. So I think the natural setting would not be like good reduction, where I assume the model is good, but a smooth central fiber, but rather I only assume semi-stable central fiber, which conjecturally is always the case. And in that setting, there is a version of this theorem.
Oh, and conjecturally is always the case. You mean that you would be able to find some integral model for which the mod P thing is sort of semi-stable.
Right.
Oh, okay, I see.
And so Chesnavicus and Kochikawa, I should say their names. So they wrote down the version of this theory in the semi-stable setting with the expected properties.
And that would need some kind of resolution of singularities, or
right.
What would be the?
Yeah, resolution of singularities and mixed characteristic would be the kind of thing that you want.
Ooh, okay.
But like in practical situations, you can probably just do it, right? Like, I mean, I'm not saying you can prove resolutions, but like if you actually have a variety, you probably can just try to resolve it.
Oh yeah, thanks.
Well, thank you very much. let's see. One practical matter. Are there any other questions first? Let me
Can I
ask.
ask one more question? Can you explain like a filtration of TP of X? Like
Are you asking me why there is this filtration that I alluded to over here?
yes.
It's a little hard to explain in short. I mean, I think we tried to write a reasonable introduction to that paper, so probably it's better to look there. But like in words, roughly what happens is that you try to cover your space by extremely ramified spaces. So these perfectoids and sort of variants of perfectoids that we call quasi-regular semi-perfectoid. But these spaces have the property that the cotangent complex is concentrated in degree 1 rather than degree 0. And then on those spaces, the filtration is just the canonical filtration of the complex. And then we do everything by descent.
Thank you.
Sorry.